Functions. What is a function? A function is a relation where every input has a unique output. What does that really mean? Let's illustrate that with a few examples and maybe some counterexamples. Suppose I have a set, and let's say I have numbers in set, say like 1 and 2. And I have a function that takes these numbers to a different set. So I'll call f my function. Or let's say f takes 1 to a, so we might write as like f of 1 equals a. And f takes 2 to b, we could say f of 2 equals b. Notice that each of my inputs, 1 and 2, go to a unique output, either a or b. That's a function. Now, what if I had something like this? We'll keep it simple for now. The function takes values or something in one set to values or something else in another set. What if I did something like this? We'll draw some lines. Well, this would mean f of 1 equals both a and b, and then f of 2 equals b. Would this be a function? The answer is no, because notice that for the input 1, we have 2 outputs. That is, for the input of 1, I don't have a unique output, which means this is not a function, even though I called it f. Let's do another example like this. My inputs of 1 and 2, and my potential outputs are a and b. And then we have some sort of relation which we're going to call f. What if I have this? And let's see what this means. This means f of 1 equals a, or f maps 1 to a. F of 2 equals a. So f maps 2 to a as well. Is this a function? And the answer is yes, f is a function. Now you might have an objection saying, but wait a minute, both 1 and 2 go to the same output. That is, we have 2 different inputs that go to the same output. How is that a function? Well, the definition of a function is each input has its own, that is, unique output, in the sense that each input is only mapping to one place. I could have something like this. 1, 2, 3, 4, and all of these map to A. That's still a function, because each input is only going to one place. But if I had something like this, where I have one input, say 1, it's mapping to a bunch of different places, this is not a function. Yes and no. Now, we're used to writing functions in function notation. We should be if we're in college algebra. Whereas something like f of x equals x squared. Is this a function? You probably know what the shape looks like. If you studied algebra at all before, we have a parabola. And notice that every input, where x is going to be my input, it doesn't matter which x I choose, there is a unique y, there's only one y that corresponds to that input. So f of x equals x squared is indeed a function. And in fact, we can find values of the function, like f of 3, for example. And to find the value of the function, we can plug in the 3, because it said f of x, which means x is now 3. So we'll plug in the 3 for every value of x, and I highly recommend that you plug inside parentheses as such. You don't always have to, but if you're unsure when you need to, when you don't, just get in the habit of plugging in inside parentheses. So if I found f of negative 4, I could say, well, x is now negative 4, so every time I see x, I'm going to replace it with negative 4 inside parentheses. So I can say f of negative 4 is positive 16. Continuing on, let's do something similar. What if I had f of x equals x squared minus x? Is this a function? Well, without drawing the picture, think of any input. You choose any input. In my mind, I'm going to choose 3 and negative 4 again. But if I choose any x value, how many different y values will I get out? And you should see it doesn't matter which x you choose, you will get only one y out of it. So if I want to find f of 3, I'm going to plug in x equals 3, because that's what I'm saying, x is now 3. Plug in x equals 3 inside parentheses for every single x that I have, and simplify. Similarly, for f of negative 4, that meaning x is now negative 4, I'm going to plug in x equals negative 4 inside parentheses for every single x in my equation given by f of x. And I can easily get values. So one thing you've probably been taught, and we're going to go back to a picture really quickly. One thing you've probably been taught about functions and determining is this a function or not, is you've used something called the vertical line test. Meaning, I have a picture, I have a graph, it is a relation. In this case, it's meant to be a circle. And if I choose any x value, and I draw a vertical line through that x value, is there only one y that I get? Or does this vertical line cross more than one point on my graph? Notice that I cross, at least at this place, 2 points. That is, for this particular x, I get 2 distinct, non-unique y values. Meaning, if I think of a graph in this way, we would say this is not a function because it fails the vertical line test. Now, I want to caution you, because the definition of a function is every input has a unique output. And later on in math, even though I might write this equation as x squared plus y squared equals, say, maybe 3 squared, I could write this in a different form, and you don't need to know this, but just to make you aware. I could parameterize this, whatever that happens to mean. And this set of parameterizations gives me the exact same equation as this would. Where in this form it's not a function. But if I rewrite it cleverly, I now have a function. So the vertical line test, it'll probably work for us in college algebra, because we're not going to talk about parameterizations. But if you go forward in math, I don't want you to think of functions as graphs in the sense of it's a function if it passes the vertical line test. It's not a function if it fails the vertical line test. Because the true definition of a function is this: a relation where each input has a unique output.